Hi, welcome to today's session. So in today's session, we are going to be looking at another important aspect of reinforcement learning, and that is the problem of the actor-critic approach. By using the actor-critic approach, we are able to optimize our policy, we're able to calculate, are we able to effectively estimate, what the expected return is, and with that, we're able to calculate the advantage to be able to, know how far it is the model is learning, basically that. Now, that also comes with some kind of disadvantages, and that is what we are going to be looking at in this session, and that is, the problem of actor-critic approach, right? Now, we've been able to establish that actor-critic is better than simple deep reinforcement learning neural network, okay? So that's better than it, but still, it has some challenges, it has some problems or some disadvantage to it. And one of the major disadvantage it has is that there's no limit on how much the policy can change. Okay. So I would say problem of actor critic. So the first challenge is there is no limit on how much policy can, right? There's simply no limit to how much the policy can change. Meaning, I'll give an example. The example is a single update. A single policy update can change or distort the length information, right? So a single policy update, a single gradient update, right, during back propagation can change, the learning, okay? And that is going to lead to something, called catastrophic collapse. So I'll explain catastrophic collapse in this way. Let's say in the first set of episode of training, let's say while training, say episode 1 to 300, okay, the model shows significant, learning by having a consistent increase in reward. So let's say we have something like here is episode, and here is R, which is reward. So we are probably able to have a consistent increase, right, in learning, right? You can see the reward is increasing from 0 here to n, right? Now, it is possible that we get to a particular point. It's possible that we get to a particular point, let's say this point, and then we have a decrease in the reward, okay? And this decrease in the reward, okay, let's say episode 301, okay? This decrease in reward is as a result of a single gradient update, okay? It's as a result of a single decrease So now let's imagine this. that as a result of a single gradient updates, the model starts declining. Okay, the model start declining, or let's say the weight changes, drastically as a result of a single gradient update. And this is possible because of, how the gradient update happens. Okay, so the gradient update happens as a result of this formula which says new weight equals old weight time minus learning rates times gradients. Okay, because this gradient has an exponential factor on the increase of the learning of the weight. Okay, so any significant updates on model weights affects learning. Okay, any significant update on this model weight affects learning, affects the gradient update. Any significant gradient update affects the learning, and that can shift the direction in which the learning approaches, or the model approaches learning. Okay, so and many times as a result of, because we've talked about in some of our sessions, I made a video on back propagation. I talked about exploding and diminishing gradients. I've mentioned this, that during back propagation, if we have large, gradient updates, that does not only affect the model because the model start forgetting what it has learned earlier, it also explodes the gradient because these gradients are just too large and it affects what has been learned before that gradient update. That's large gradient update. So it's a very significant problem in deep learning. Now, so I was talking about if we have a large gradient update. So there are there are some things that it affects generally. One is the weight changes drastically. And you can see that through the formula I highlighted here, that since the weight has an exponential, factor, has a multiplicative factor on the weight. So if this is large, you can always expect this to be large as well. So if you have a large gradient update, then definitely you are going to have a massive weight update as well. Then also the policy becomes different. Don't forget that this policy will be learned across, different states, different states, okay, of the environment. So if you have significant gradient updates as well, it affects the policy. It affects what has been learned earlier within the policy environment. Okay. Also, learned behavior is lost. So that is what has been learned earlier. That is what has been learned earlier, during gradient updates is often, lost as well. Then also, agent has to start from near scratch. Okay, agent starts from near scratch. So, and this leads to, a problem called catastrophic Okay, this leads to a problem called catastrophic forgetting because significant gradient updates affect everything that has been learned earlier before then. Now, and we know that the bigger the advantage, the larger the gradient. As a result of the actor-critic approach we looked at earlier, the bigger the advantage, the larger the gradient. So, in a single episode, when there is a large advantage, then also a very large gradient update happens, and that can lead to collapse. Okay, you know that the larger the advantage leads to uh, larger advantage leads to what? Larger updates. Okay, and this large update can we've been able to establish that this can lead to collapse of learning. Okay, now all of this problem is going to lead us to something called KL divergence. So what is KL divergence? So KL divergence, helps to measure, how different two probabilities are from each other. Okay, because at the end of the day, we have two different distribution. One is the estimated one, the other one is the actual return, and all of these are, we compute both of these to get the advantage. Now, here, because we've been able to realize that, well, estimating the advantage is not enough. It's not enough because of the issue I just explained about catastrophic forgetting. You know, if you're able to have a significant difference between both estimated and actual return, between the actor and the critic, leading to significant advantage, that can lead to significant gradient update and catastrophic forgetting, which we want to avoid. So how do we avoid that? We are going to look at the approach of KL divergence. So KL divergence now helps us to measure the distribution of both networks, the actor and the critic, for example. And I'm going to give a formula for the KL divergence. So you say KL divergence of policy O, right? To the policy new equals to the summation okay, right? So this is basically KL divergence. So KL divergence helps to measure the probability between the old distribution and the new one, right? And while doing that, we are estimating the summation of the policy, the gradient policy of the old, and that of the new, multiplied by the log probability of that of the ratio. We are going to talk about the ratio, which is this. I'm going to refer to this as ratio. So just let's note this. This is the formula for KL divergence. We are going to look at this. But there's something I want us to have in mind, before we proceed. Now, if KL is equal to 0, right? This means if KL is equal to 0, it means the distributions are identical. However, if KL is large, I think we can guess that the distribution are different. Okay, we can note here that the distribution are what are different. Okay, now there's something I'm going to be talking about here. Let's take a look at an old policy. So don't forget that this is old policy, this is new policy. Policy aligns information over time. Across the episode, the model keeps updating its policy. Policy are like action to be taken at what state. We've talked about that in our previous sessions. Now, let's take, for example, you have a policy, let's say old policy. Okay, the old policy was in a particular state, given a particular state, on the left, the probability of going to left is what? Is 30%, for example. Probability of going right is, let's say, 70%. So this is what was established before. Now, after a small update, let's say after okay, if we have after the small update, after small gradient updates, variable propagation, we got that okay, the parameter of going left is no longer 30%, it's now 25%. Right? A probability of going right is now 75%. Well, you will agree with me that the difference between both of them is small. And as a result, this is small gradient updates, which still keeps the KL divergence to be safe. Okay? Because in KL divergence, we are measuring the difference between the probability of these two different distributions. And since the difference between them is small, right, we can say this is safe. KL divergence helps to measure, the difference between two different distributions to see how far apart they are. We mentioned earlier that if the KL is small, which you want to maximize, we want to ensure that they are as close as possible to each other. So when the KL is small, then that is safe. But imagine we have an update that after an update, probability of going left is, let's say, 85%. The probability of going right is, let's say, 15%. You will agree with me that the particular distribution from this is very large. So when we are measuring the KL divergence, we realize that this is large and dangerous. Because these two different, if you are having an update of this on top of that, that can lead to catastrophic forgetting, because what has been learned earlier is much different from what we have now. And that can lead to catastrophic forgetting. So when we have smaller gradient updates, that's safe for learning. But when you have larger gradient updates, that is very dangerous for learning. That can lead to the model, the policy being significantly changed, and the model forgetting what has learned, so far. Now, that is what we want to do with scale divergence. So in Actor-Critic approach, there's no constant KL that's being used to maintain the difference between different distributions. So meaning when we have large, when KL is very large across distribution, we can have a collapse, which I've explained earlier. And now we are going to be proposing a particular solution. And the solution we are proposing is PPO. Okay? PPO meaning Principal Policy Optimization. Okay, PPO meaning Principal Policy Optimization. So, which you are still going to look at now. Now, let's take a look at, so I was talking about this particular ratio earlier. Let's take a look at this ratio now. Now, this ratio, I'll call it RT, is equal to the distribution of the new, is equal to the new policy Okay, new policy of a given action given a state. Sorry, of an action given a state divided by old policy of an action given a state. So that is that. So R of t, which is reward, time-based reward, equals to the new policy of an action given state divided by the old policy of an action given a state. So this ratio measures how much policy have changed, for a particular action, a single action. So I'll say measures how much policy has changed for an action. Okay, because with this, we're able to measure the difference, right? We're able to measure the ratio between new and old policy by simply dividing them. Okay? Yeah. So you're able to do that. Now, so we will not just be doing this way. Okay, we are going to be using log. We are going to be applying log transformation on top of this to be able to measure how much the change has happened between the new and old policy. And to be able to do that, we are going to say R of t is equal to exponential logarithm of, I can write it this way. Okay, minus log of actually states, right? So this is basically how we measure the log probability as the difference of two different policy distribution between the old and the new policy, right? Using log probabilities, we're just logging it. Now we have a logarithm log policy of the from the training loop. So RLT, just compute on top of that. So what we have here is now that if R of t is close to 1, right? If the ratio is close to 1, it means for all actions, so then the policy value change because the KL will be small. So of course, if you are finding C, if you have two different distribution between this, if this to this is 1, that means it's the same thing, just like saying 3/3 equals to 1, right? So if the ratio, if ratio is 1, right? What that means is that KL is small. Okay? That means KL is small and policy barely changes. Policy barely changes, right? Now, if R of t is large, so what that means is that the policy changed a lot and KL is large, right? So that is basically what I want us to take away from that. Now, so how do we keep this to, how do we keep it between between being small and between large? Because we don't want it to be small, we don't want it to be too large. We want to optimize it, being as small as possible, so that we can have steady increase in the gradient update. Not that we don't want gradient update, of course, that's the purpose of learning, gradient update, but we do not want to have large gradient updates that distort the learning process or that leads to catastrophic forgetting. You don't want to have large gradient update. That's the point of measuring all of this ratio, KL divergence, and the likes. Okay, so how do we keep this within a measurable, between a measurable interval? Okay, so keeping, I'm going to now say R of t near 1, okay, is going to lead us, that is keeping KL small. Okay, keeping KL small will lead us to PPO, and PPO will help us to keep KL, sorry, you help us to keep R of t to the ratio between 1 minus exponents and 1 plus exponents. Okay, so people will help us to keep our policy, will help us to keep our return between 1 minus exponents and 1 plus exponents. And this particular action of keeping the return between that measurable difference is known as clipping. It's known as clipping, right? So now let's take a look at our code. So you're going to be going to coding right now. The first thing I'm going to be doing here is I'm going to be importing important variables. I'm going to be importing important libraries which we are going to be using. The first of which is NumPy, Matplotlib, Touch, and Touch here, right? Now, the next thing I'm going to do is I'm going to create a function that helps us to plot catastrophic forgetting. So how I want to do that is this. Now let's take a look at this. So this is going to be plotting of catastrophic forgetting. So you're going to take n, which is like number of episodes, to be 500. Have a reward here in an empty list. You have a return here initialized to be 30.0. Now you have a for loop that iterates over this n, right? Now if so here we have R plus, so we are increasing return by um, a normal distribution of between 0.5 and 8, right? So we append that to our return. We increase that by our sorry, which is our return. So with that, what we are going to be having is we are going to be able to see that increase, okay, in the value. We have that steady increase in the value of R, which is the return or the reward. Okay. Here we have R equals to the clip R 5 and 500. So we are able to establish R between, um, limited range, okay, steady increase of the value of R within that limited range, okay. Now, so what I try to do here is when the iteration, when I reaches 300, so because it is increasing, you realize that R was increasing. We are iteratively increasing the value of R. But when R got to 300, R becomes 30, meaning it is going to drop back at some point. Okay, dropping back at some point, and then also when I reaches 420, then R is 25. So you realize that if R was able to, okay, you're going to see the visualization, where R is going to reach 300, steadily increasing up to 300. And when it reaches 300, we drop the return to 30. And when it reaches 420, we drop the return to 25, which is exponential updates. I mean, significant update of the gradient update. And that could lead to, forgetting or decrease in the return. Forgetting, decrease in return. So basically, that's just a minute. So we find my way around this. Now, take a look at this. Take a look at the graph that we have here. So realize that we have a steady increase in reward with episode or with time. And then when we got to this particular episode here, at episode 300, you realize that the reward came down. And then while the reward is trying to come up again, it's trying to increase. Okay, so it came down here and trying to learn back again. Well, so basically what we are just having here is, so you realize that at this point as well, it came down, at 425, it came down as well. So you realize that there's no steady increase in the rewards, and that depicts the learning rate as well. I mean, how well does this model learn? How do we observe its learning? We observe that it learns through the rewards it's able to obtain over, the episode, right? And when you're having this kind of sharp decrease in reward, just like you can see here. So it depicts a large gradient updates that distort the learning process for this model. So we are going to be looking at another example as well. And that is going to be the visualization of the KL divergence. So let's take a look at this. Now let's take a look at this. So you realize that for the old policy, probability of moving right for the old policy was 70%, for left 30% on the old policy, right? Now, when we have a small update, so this is a small update, realize that, from 30% it decreased to 25%, and from 70% on the right, it increased to 75%. So this is small gradient updates, on the policy, updates, small gradient updates on the policy that influence, of course, on the policy updates. And then by the time you compute the KL divergence, you realize that we have small gradient updates. And as a result, the KL was quite small, close to 1, right? And you can see here you have on the left, it's 5% on the left and 50% on the right. So that's basically that. This is measuring, how, sorry. So when we had 30% on the old policy left, 75% on the old policy right, and when we had a small update, I mean, this shifted from 30 to 25, 70 to 75. This is a small variance update, and as a result, the KL was small. Okay, that's the KL, measuring how the difference between both distributions are. Now, when you had a large variance update, on the left you have 85% and on the right you have 15%. So that shows a very significant change in the in the update, a very significant graded policy update. So as a result, you can see the KL divergence is significantly large. So that's basically, how KL divergence is measured, the distribution between two different, the interval or the difference between two different distributions. Now we are going to look at something else as well, and that is the probability ratio. Now let's take a look at this. So here you realize here is the ratio, which is the ratio is basically the difference between the new and the old, which is basically just the division of both. So when you have one, that shows that's very, very, very close. That is the same, right? That's literally the same. So meaning you try to optimize for having up to one. This is the backbone behind, KL divergence, dimensional distribution is good distribution. So now this is the ratio here, and this is the objective value. So you realize that when we have one here, this one here shows the optimal value. That is when both the new and the old policy are the same. Okay. So now for unclaimed value, so these are the unclaimed value here. Now when it is, so this is the safe zone between y minus e, which is the exponent, and 1 plus e, which is this. So this is the safe zone that the PPO try to clip the ratio between. It tries to clip it within that safe zone so that we're able to maintain the advantage of the return, the advantage or the KL divergence. We're able to maintain them. We're able to maintain our updates basically. Let me use too much words. We're able to maintain our updates within a significant, safe zone, between that boundary, so that we don't lead up into, catastrophic forgetting or significant variance updates that distort the entire learning process. So this is basically that. So the PPO helps to clip within this safe zone and not just returning anything possible. So that is that so far. So if you've been able to learn from what we have done so far, kindly like, share, and subscribe to this channel. Thank you.